Hello and welcome back to my Physics Online Video Lecture Supplement series. In today's video, I wanted to continue my lectures on energy and its conservation, and specifically in today's lecture, I think we're ready to look at the conservation of energy. So there's two basic types of system which we might consider in physics, broadly speaking. The first is an isolated system, which is a system in which no energy can leave by crossing the system boundary. And that means basically that you have some system that's not going to interact very much with its environment. And these are systems which generally are very nice for making models. Conservation of energy works very nicely within an isolated system of this sort. But in practice, we usually end up with what's called a non-isolated system. And that's a system in which the system of interest might interact with outside elements of the environment. And so ultimately that means that energy can enter into our system of interest or it can leave from our system of interest. So let's look at how energy might leave a system. So this is any kind of non-isolated system. You can lose energy, or for that matter, gain energy within the system. And there's a variety of mechanisms by which this happens. I'm going to mention 6 of them. So the first 3 are work, mechanical waves, and heat. So work we've already studied in depth in the previous lecture. Basically, a force is applied to the system or an object in the system, and it is applied over some displacement. Mechanical waves we will probably actually talk about as such next semester. But basically, energy can be propagated via any disturbance within the matter of a medium. So mechanical waves include everything from vibrations like in an earthquake to sound, for that matter. And so energy is lost from the system anytime that, let's say, maybe 2 cars crash against each other in a system. Well, you hear the screech of tires and you hear the sound of the 2 crashing. That means that some energy has been lost from the system just by those 2 sounds. Heat, we look at in the lab that goes with this course, though we don't usually get to talk much about it in the lecture part of the course. Heat basically you could think of as energy that's being transferred from high temperature medium to low temperature medium. So 3 more mechanisms for transferring energy into or out of a system. You could have matter transfer, so that's literally means that the matter in the system crosses the boundary of the system. For example, maybe you have air that's trapped inside of a balloon and the balloon has a little leak in it, so some of the air gets out of the balloon. That would be energy being lost from the system via matter transfer. There's electrical transmission, in which energy can leave the system via electrical current. Perhaps you have a system that you don't actually have grounded, let's say. So maybe you end up having some energy leave your system because you grab onto an electrical wire by a mistake. Or maybe the electrical wire within your device might have broken and so be in contact with the device, and the device is not well grounded and not designed very well, so it gives you a shock. And then electromagnetic radiation is another means of transferring energy. That's basically energy being transferred by any kind of electromagnetic wave. That includes everything from visible light, as in this picture, to X-rays, to radio waves, to microwaves, etc. All right. The concept of the conservation of energy means that energy is not being created and it's not being destroyed. So if you have an isolated system, that means that energy within the system will change form. So for example, you can have an object which is moving and it comes to a ramp and it moves up the ramp. Even if the ramp is frictionless, the object may eventually come to a stop at some point on the ramp. And that means that the kinetic energy has all been changed into gravitational potential energy. Energy can leave or enter a non-isolated system by crossing the system's boundaries, of course. So if you don't have an isolated system, it's not that energy is being created or destroyed, it's that you're either losing energy to the environment or gaining energy from the environment. And as far as isolated systems go, the universe is about as big as it gets, and by definition, I suppose that would be an isolated system. But it's rare that you get much else that would count as an isolated system on any scale. The basic equation that goes with conservation of energy in any case is that the change in energy for a system should be equal to the total energy which has been transferred to or from the system. So that again is going with energy is not being created or destroyed. If your system has lost energy, that energy might be found by the environment or vice versa. The work energy theorem is something that we talked about a bit in part 1 of this set of lectures. And if we combine that with potential energy, we can get sort of a single theorem, which would be the conservation of energy. Is basically, ultimately, we just say that the initial energy plus any energy gained from outside the system should be equal to the final energy plus any energy lost by the system. And this is just another way of rephrasing that previous equation, that the total change in energy for the system should be equal to the total energy transferred in or out of the system. If you have an isolated system, notice that that means that the gain and the loss should be 0. It just means that the initial energy and the final energy should be equal. So here is a nice long formulation of the law of conservation of energy. Basically, this long equation is trying to account for a variety of different types of energy. For example, this is the initial kinetic energy, the initial potential energy, work done by any non-conservative forces that are propulsive in nature, any other kinds of energy, largely energy that's coming into the system from outside, if you will, or leaving from the system. And that should be equal to the final kinetic energy plus the final potential energy plus the work done by non-conservative dissipative forces, like friction, for example, in this diagram, plus any other forms of energy that you might have in or out of your system. And so this other energy term is sort of your transferred energy that either enters the system from the outside or leaves the system to the outside. And some of that, by the way, happens depending on what system you've defined. If your system of interest in this picture is, say, this rocket sled, then you're not really counting the rails or the ground, and so any friction between the rail and the rocket sled could be energy being transferred outside of the system via heating the rails, for example, or via the screeching sound that this thing might be making as it slides along the rails, etc. So let's look again at this picture and see if we can identify where different forces are and what they count as in this equation. Well, T is basically stands for thrust. It's basically the force that's being applied to the back of this rocket sled as it propels its rocket fuel as gases. And so basically this is a non-conservative propulsive force and therefore is doing work in a non-conservative propulsive manner. There is some weight for this rocket sled, so it could have a non-zero potential energy from gravity. There is friction, which is opposing the sled's motion. That's work being done by a non-conservative dissipative force. And of course, as the rocket is moving, it will speed up, and so the kinetic energy initial will increase to whatever the final kinetic energy is as the speed of the rocket increases. And I suppose you could also say that there's a slight decrease effect as well, because as this rocket burns through its fuel, the fuel is ejected and the mass, therefore, of this rocket actually gets smaller. Overall, though, I think if the system is just the rocket itself and whatever's inside the rocket, you basically have an increase in kinetic energy, though again there is going to be some energy lost because some matter is leaving the system. So we've talked briefly about non-conservative and conservative forces in part 1 of this lecture series. Recall that a non-conservative force is a force which will do a different amount of work to get from point A to point B depending upon what path it takes. So, if you go from point A to point B in a straight line, you're going to get a different amount of work done by, say, friction than if you do some sort of a curve to get from A to B, a not very direct route. And so what these non-conservative forces do is they change the amount of mechanical energy which is in a system. Now, mechanical energy is generally taken to be the sum of the kinetic energy of the system plus the potential energy of the system. And what figure 7.3.5 is actually a sort of analogy for non-conservative forces. Imagine that this is an eraser that you're dragging from A to B. Well, the amount of the picture which you erase is going to change depending upon what path you take from A to B. So if you rub the eraser back and forth a lot to get from A to B, you'll erase a large portion of the picture. If you just drag it once from A to B, you don't erase very much of the picture. The picture in this case basically represents the total amount of mechanical energy that the system has. And so the part that you're erasing with this eraser is like work done against the system by friction. It's sort of depleting the amount of total energy that's left in the system. The friction, by the way, is one of the more common of the non-conservative dissipated forces. And the work done by friction is generally going to be given by the force times the distance traveled. The reason why it's not conservative is because the path you take now matters. Recall that displacement does not care about path taken, but distance does. So if I were to drag the mouse from one corner of the screen more or less straight to the other corner, I've taken one particular path to get from point A to point B. On the other hand, I could also get the same displacement by dragging along one side and then dragging down the other. I've got the same displacement in both cases, but I went a much greater distance by going like this than I did by going directly from one corner to the other. And friction itself then depends upon two things, as we saw in the forces lecture. It depends upon the coefficient of friction, and it depends upon the normal force between the two surfaces that are sliding against each other. The normal force in turn depends oftentimes on the weight of the object and also the angle of incline, although there are plenty of counterexamples. For example, if you were to hold the block up against the wall, you apply a normal force to that block that is completely independent of the weight of the block. It's just dependent upon how hard you press on the block against the wall. Or a vise, for example, when it's holding something, applies a normal force that depends upon how much you tighten the vise and not on how much the object weighs. But very often we're dealing with an object that's sliding across the ground or sliding up a ramp or a hill or what have you, and then the weight basically helps determine the normal force. So let's look at a few relatively short examples. We'll do all three of these in turn. So let's start with this one about a block that's sliding along a level surface with a given coefficient of friction. And we want to know how much work the friction will have done after the block slides for 4 meters. So this one is a relatively straightforward example. In fact, we could have just as easily done this in part 1 of this lecture series. Basically, you have a block which has a 25 kilogram mass, so 25 kilograms here, and it slides over by 4 meters, so the block ends up over here, 4.0 meters. And we want to know how much work is done by friction. So since the block is basically moving in this direction, friction is going to be acting in this direction. How much work is done by friction in this case? And work is basically going to be given by force dotted with the displacement. So what that basically looks like is displacement is this way, force is this way, the angle between them is 180 degrees. So this is just going to look like force of friction times the displacement times the cosine of 180 degrees, which we can just ignore, is basically equal to -1. So we can just put that as a minus sign here. And then force of friction, of course, in the case of a block that's sliding, is going to be the normal force times the coefficient of friction. Presumably this is the coefficient of kinetic friction. So this is mu. So this basically looks like mu times m times g times cosine of the angle of inclination, which is 0 degrees. So again, this can go away because it's just equal to 1. And so this is 0.18 times 25 kilograms times 9.8 meters per second squared. So that gives us a total gives us a total force of 0.18 times 25 times 9.8 gives us 44.1 newtons. So we have force of friction, 44.1 newtons, and therefore the work done by friction should be 44.1 newtons times the displacement, which was 4.0 meters. So we can basically take this guy and multiply by 4, and we get 176.4 joules. So basically 176.4 joules should be only 2 significant figures, so we could write that work is 180 joules approximately. And there we have it. Second example, what's going to happen in the above example if this block is sliding up an incline of 5 degrees instead of sliding along flat level ground? Well, if that's the case, then let's go ahead and just draw ourselves a nice little diagram here. So this is a 5-degree incline. The block is sliding up, so this is the direction that it is moving. Therefore, friction is down along the ramp. So that's force of friction. Here's gravity, so force of gravity. Here's a badly drawn normal force vector. And so there's really two things that change here. One is that gravity is now actually doing work on the object because there's some component of gravity which is in the direction or against the direction that the block is moving in. So we could write, for example, that the work done by gravity should be mg times, so if this is the delta x direction, it'd be delta x times the sine of this angle theta, where this right here ultimately gives delta h. So this direction right here is the delta h direction. This right here is the delta x direction. And then out of or into would be the delta y direction. So notice that delta h and delta y in this geometry are not going to be the same. That aside, though, the question's really asking what changes about the work done by friction. So work done by friction is still going to be F dot delta R, and that becomes F times delta X. But now this force of friction, which before was basically given by the normal force times the coefficient of friction, where the normal force was the weight, we now have to include the angle of the ramp in that normal force. So the normal force is mg times cosine of theta, and we cannot just cross out the cosine theta as being 1, because instead we have mu times m times g times cosine of 5 degrees. So m is the mass, again that was 25 kilograms. G, of course, is the free fall acceleration, 9.8 meters per second squared. So we can now calculate this and recall that this guy was 0.18. So we have 0.18 times 25 times 9.8 times the cosine of 5, which is almost 1. You get 43.9. So this is roughly 43, we'll say 0.93 newtons. And so the work done should be that force times the distance traveled. Distance traveled was 4 meters. So 43.93 newtons times the 4 meters. And what that's going to get us now is 175.7. So 175.7 joules. Of course, again, we only have 2 significant figures to work with, so we actually would write this also as 180 joules. So if we're being sticklers for significant figures, the answer is nothing changes as far as the work done by friction is concerned, although now we have to include some work done by gravity. But, and by the way, you can figure out how much work is done by gravity here. Fairly straightforward. The mass is 25, gravitational acceleration is 9.8, the distance is 4, and then we're multiplying that by the sine of this angle. And so you get 85.4 joules from gravity, as opposed to 0 joules from gravity in the previous problem. So if we're being sticklers about significant figures, this is the only change. Now, if we're not being sticklers about significant figures, we notice that this number is slightly smaller than the one in the previous problem. In fact, it's about a little under a joule difference. So that's what changes if you make the block slide up an incline of 5 degrees. Okay, and for our third example, how far does the baseball player travel before stopping if his initial speed is 3 meters per second? So if you look at this figure, you can see that the force of friction is given as 850 newtons. And the question is, how far is this guy going to actually go before he basically gets to stop? So the baseball player has a known amount of friction working upon him, 450 newtons. So let's just go ahead and write force of friction equals 450 newtons here. I'm just pulling that off of the diagram. And our conservation of energy says that the change in the kinetic energy plus the work plus change in potential energy for an isolated system should be 0. So we're taking this to be basically an isolated system wherein any energy lost is coming through from this work done by friction. So that means that we need to basically find how much work is done by friction in order to change the kinetic energy via changing the speed from 3 meters per second to 0 meters per second. So work done by friction is going to be this force of friction times whatever distance that he slides along. So we'll just say force of friction times delta x. And then change in potential energy is going to actually be 0 because he's not changing height. There's no springs attached, nothing like that. So we need to look at what the change in kinetic energy is. So delta E for the kinetic energy is whatever 1/2 the mass times the final speed squared minus 1/2 the mass times the initial speed squared. So this final speed squared is 0 because he's stopping. This right here is the initial speed, and we're given the mass as 70 kilograms. So this looks like 1/2 times 70 kilograms times 3.0 meters per second squared. So basically you end up getting 0.5 times 70 times 3 squared, 315. So the change in kinetic energy should be 315 joules. That's equal to the work. So we can write force of friction times delta x is delta EK. And so that means if we divide both sides by the force of friction, then you've got delta x. So this is 315 joules divided by 450 newtons. And so you get delta x is approximately equal to 0.7. So he will slide for 0.7 meters, which I suppose is not actually very far of a slide, all things considered. So probably what this implies is that the force of friction between a baseball player and the ground is somewhat less than 450 newtons while the baseball player is sliding, because 3 meters per second is a pretty decent clip. You know, maybe you can go half again that usually before diving. Maybe a full sprint might be twice that, in which case this number is 4 times bigger, and so this number is 4 times bigger, and you're at 2.8 meters. That's a little more believable. So that's a relatively simple conservation of energy problem that we just worked. And in fact, that last one, again, could just as easily have been worked under the work energy theorem. Usually, conservation of energy itself tends to come in when there's multiple forms of energy, and that may be in the sense of having multiple forms of kinetic energy plus some potential energy, or it could be multiple forms of potential energy plus some kinetic energy. It could involve work plus potential energy plus kinetic energy, as with that ramp problem that I did earlier, with the blocks sliding up the ramp at an angle, etc. So one example then, or I should say another example then, might be this spring-loaded pop gun. And you can see that there's 3 types of energy that could be involved in this system. If you've compressed the spring, then it is storing some elastic potential energy. The spring will be doing some work against the ball when the trigger is pulled to fire the ball. That means that the ball is gaining kinetic energy in the form of a change in speed. It also, there may be friction with the barrel, so that's a 3rd type. And then if you're firing vertically like this one, you get a 4th type, which is that you're changing the height and therefore the gravitational potential energy. So you can see that there may be as many as 4 terms within your conservation of energy equation. So conservation of energy lets us build up a strategy for how to approach problems of this sort. So one version of the strategy is that you choose you're allowed to choose a point where the potential energy function is 0 for any given potential energy. And you're allowed to choose that once for each type of potential energy. So you can choose the potential energy to be 0 for the gravitational energy when the ball is at the bottom of the spring's motion, for example. You can choose the potential energy to be 0 for the spring at the moment when the ball leaves contact with the spring. So it's also worth noting where in this problem the ball will have 0 kinetic energy. And there's actually 2 places. Once right before it's fired, and then once when it reaches the top of its motion. So maybe the ball gets up to here before falling back to the ground, before moving towards the ground. And so oftentimes it's useful to solve for the potential energy values first at a given position, then figure out how much work has been done by a non-conservative force, such as friction, and then whatever's left over gives you your kinetic energy. So if I were to fire this pop gun, I might start with some potential energy from the spring. I have some potential energy from gravity. Friction may or may not do some work against the ball, and then the ball is going to launch. And notice that the work done by friction should be linearly proportional to the distance along the barrel that the ball has moved. Work done by gravity is linearly proportional to the distance along the barrel that the ball moves if the barrel is pointed upward, but it's also linearly proportional to the upward distance in general. Work done by the spring would be a quadratic with the distance over which the spring is in contact with the ball, and then all of these different energies combine, and whatever's left over from what we started with, that's what is left for kinetic energy. And some authors will put what might be called an energy states plot or an energy bars plot or some various names of that nature. They basically look like this, and it's just there for us to visualize exactly how much energy is in the system. And they break down, this is, for this pop gun, they've broken it down into two components. One is the non-isolated system. So initially you've loaded the ball into the gun and there's zero energy, and so we've set gravitational potential energy to be wherever the spring and gravity are at equilibrium with each other. So whatever the spring compresses to when the ball is just simply dropped into the chamber, that's the zero potential energy, total potential energy. That's gravitational energy zero, that's spring energy zero, etc. So it's non-isolated because presumably you then have to cock the gun. Basically, you have to compress the spring so that it's ready to fire. And by doing that, you add a bunch of elastic potential energy, and you also take away a little bit of gravitational potential energy. Again, we're assuming the gun is pointed upward as in the previous figure. So you've added to the total energy of this system. If you take the gravitational potential energy and you add it to the elastic potential energy, you get this total energy. And once you've done that, if you don't touch anything save the trigger thereafter, you have more or less an isolated system. This bar graph, by the way, is assuming it's a frictionless pop gun. So essentially, you fire the gun, the shot moves upward, the elastic potential energy starts decreasing, the gravitational potential energy starts increasing, the kinetic energy starts increasing. And since we defined the gravitational potential energy to be zero at the moment when the spring and gravity are in equilibrium, well, in that particular moment, all the energy has to be kinetic energy. So that's how you get the initial kinetic energy from this system. Then the ball travels upward. There's no more spring on it, so the elastic potential energy stays zero. The ball goes up, 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 up. The kinetic energy starts decreasing. The gravitational potential energy starts increasing. And at the point when the ball gets to the highest part of its motion, the kinetic energy goes to zero and the gravitational potential energy is equal to the total energy. All right, so that's kind of a lot of words without a whole lot of writing. Let's look at a few short examples with this. So let's say that we take the pop gun and we load it with a particular pellet. And we're going to assume that the pellet does not rotate, because remember, if it rotates, then there's some rotational kinetic energy. So we compress the spring by some amount. We give the spring, therefore, some amount of energy. And we want to know what's the pellet's speed as it passes through equilibrium. And from that, can we figure out the pellet's maximum height? And what happens if we include friction. This pop gun has been loaded with a 1 kilogram pellet. So let's go ahead and write out that the mass is 1.00 kilogram. The pellet is being fired from rest, so we'll say that the initial speed is 0. We don't know what the speed is at equilibrium, so that's the thing we're actually looking for. So that's what we've been given kinetic energy wise. So this is, let's say, EK. For the spring, we've been given that the initial spring energy is 100 joules, and that this spring has been compressed by 0.25 meters. For gravity, what we've been given is, if we're going to define this equilibrium position as x equals 0, so this is equilibrium, then this also means that this velocity here is the equilibrium velocity that we're looking for. Notice that by compressing this, we've actually dropped by this amount for gravity. So the initial gravitational energy should be m times g times delta x, where for gravity's sake, delta x is minus 0.25 meters. Okay, so let's go ahead and get all of the initial energy conditions. So the initial kinetic energy is 0 because the ball is initially at rest. The initial spring energy is given as 100 joules. You may, by the way, be wondering, what is the spring constant? Is it an ideal spring or a not ideal spring, etc.? Turns out we don't actually need to know that information to do this problem, because we've been given this initial energy and we're asking for what happens at equilibrium. So this is the initial. The final spring energy, we'll put EQ for equilibrium, we can effectively say is 0. And for gravitational potential energy, I've now given all the information we need to solve for it. Is basically 1 kilogram times 9.8 meters per second squared times negative 0.25 meters. This is the initial gravitational energy. So got to calculate this guy. It's basically 1 times 9.8 times 0.25, whatever that number is negative. So initially we have a gravitational energy of negative 2.45 joules. Finally, we're at x equals 0, so the potential energy for gravity at equilibrium is also going to be 0 joules. Okay, so this means initially we have an energy of 0, so basically EKI plus ESI plus EGI. And so that is 0 joules plus 100 joules minus 2.45 joules. And so initially we have a total energy of 97.55 joules. That means that finally we have 97.55. So finally, and that's at equilibrium, we have that EK equilibrium plus ES equilibrium plus EG equilibrium also needs to be 97.55 joules. But we already determined that, so by definition, when we're at equilibrium, these two can both be zeros. So in other words, we've used up all of our potential energy, so that means that the kinetic energy is 97.55 joules. And kinetic energy is given by 1/2 times mass times speed squared. So if we're looking at equilibrium, then we just put in the equilibriums here. And so the speed at equilibrium, if we're going to solve for this, we need to multiply by 2, divide by m, and take a square root. So we have 2e sub k eq over m, and we have to take our square root. And so that is square root of 2 times 97.55 joules divided by the mass is 1 kilogram. And so this means that the equilibrium speed is approximately equal to, okay, so 2 times 97.55 gives us 195, divided by 1, take a square root, 13.97. We've got 2 significant figures to work with, so this is basically 14 meters per second. So now we have the equilibrium speed of the pellet. All right, so the next question was, what's the pellet's maximum height going to be given this information? So again, recall that we've taken x equals 0 to be the position of the pellet at equilibrium. So we're basically looking for x equals x max. And to do that, we basically, so we now have this kinetic energy at this point. E kinetic at equilibrium had to be E of everything initial, or E at equilibrium is E initial. And that also has to be equal to E final. And so, and of course that was 97.55 joules. So that means that at the maximum height, all the energy is going to be in potential energy. So at this, we have V equals 0. So E final is E gravity final. And that has to be equal to E initial, or E equilibrium, or energy anywhere else in this problem. Okay, so this now means that we go and we use mg x final is equal to this final energy, and so x final is whatever this final energy is over mg, so that gives us 97.55 joules divided by 1.00 kilograms, because that's the mass of the pellet, times 9.80 meters per second squared. So that means that our final height should be, or our maximum height, I should say, should be, let's go ahead and pull out the calculator. So 97.55 divided by 1 divided by 9.8. Oops, 9.8. And that says 9.95 meters. So again, we have to round. So this guy says 9.954 meters, should round to 2 significant figures once again. So really our final is 10 meters. So the pellet should end up 10 meters above this point that's called the equilibrium point. All right, so last but not least, what happens if we include some friction in this problem? So Specifically, if we're going to include friction, then we need to now have 2 newtons or some given force of friction. So this would be force of friction. And we need to have a length of the barrel. This 0.75 meter long barrel thing is basically saying from the point where the thing is launched from to the end of the barrel is, we'll call this x sub b for x barrel, 75 centimeters. Okay, so to actually solve this, the process is very much similar to what we did before, in which we have our initial energy, and we already solved for that as 97.55 joules. That is gravitational energy plus kinetic energy plus potential energy. And what we do is we go ahead and solve for basically we could go about solving for what's the speed here, because that's one of our previous answers, and we can go ahead and solve for the maximum height. So at this point, the equilibrium point, we would write that E at equilibrium plus work done by friction up to equilibrium should be equal to the initial energy. All right, well, the work done by friction is going to be force of friction times the distance traveled to get to that equilibrium thing, the equilibrium distance, so delta x to equilibrium. So that is 2.0 newtons times 0.25 meters. Recall that this initial distance here was 0.25 meters, and similarly this had a 1.00 kilogram mass. All right, so work done by friction to get to equilibrium should be 2.0 newtons times 0.25 meters, so that should be 0.5 joules. So work done by friction to equilibrium, 0.5 joules. Therefore, the leftover energy at this point, E at equilibrium, should be 97.75, E initial, minus this work, 0.5. So 97.55 joules minus 0.50 joules. So that means that the energy at this equilibrium point is down to 97.05 joules. Okay. So at equilibrium position, again, there's no energy in the spring and no energy in gravity. So the energy at equilibrium is entirely concentrated in kinetic energy. So we can write EK, EQ, so that's 1/2 times mass times speed at equilibrium squared. So again, speed at equilibrium, we can take multiply both sides by 2, so we'd have 2 times E at equilibrium divided by the mass and with a square root. So that is square root of 2 times 97.05 joules divided by 1.00 kilogram. And so we can take those guys in. Let's do 2 times 97.05 divide by 1 and take a square root, 13.93. So VEQ 13.93198 meters per second. Again, if we only have 2 significant figures, this right here becomes 14 meters per second, which is actually the same answer that we had in the previous problem. So that didn't really change to 2 significant figures if we included some friction. So let's go ahead now and figure out how high the pellet is going to actually travel. Well, we're going to have to figure out how much more work is done by friction in getting from equilibrium to here, which is 0.5 meters worth. So we have an additional work, let's say work of friction total. So that would basically be from here to here. So we don't really have to calculate this part if we just do this one instead. It's sort of your call. I'm going to do this because it's easier notationally. So we'd have force of friction times delta x total, and so that is the force of friction times x barrel, which again is 0.75. So we would have 2.0 newtons times 0.75 meters, and so the total work done by friction should be 1.50 joules. Okay, that means that the total energy left over at the top, let's call that E final, not to be confused with work done by friction. So this is a capital F in case you can't understand my very sloppy handwriting. This is a lowercase f for final. This final energy has to be equal to the initial energy minus the work done by friction total. And so this right here, therefore, is going to be 97.55 joules minus 1.50 joules. And so the final energy, once it leaves the barrel, has to be 96.05 joules. And that then we can set equal to mg x final. Because when it gets to the top of the motion, there's no kinetic energy, so it all has to be potential energy from gravity. And so x final must be E final over mg, so that's 96.05 joules divided by 1 kilogram times 9.8 meters per second squared. So let's see if this one ends up being any different. So let's see, there was 96.05 divided by 1 divided by 9.8, and we end up with 9.80. So this we can round to 9.8 meters. So final height 9.8 meters. And remember that in the previous one, we had a final height of 10 meters when we went to 2 significant figures. So there is some actual difference that you can see from friction. It's not very much, but it is measurable, even with 2 significant figures. One application for conservation of energy is that it makes it a little bit easier to determine the escape velocity that we need for basically how fast an object needs to be launched at from the surface, or for that matter from the center of the Earth, in order to basically escape from the Earth's gravitational field. Those of you who are in general physics, this D is a typo for delta. So we're looking at changes in R, changes in path length for the object, but this is basically the kind of diagram that we might use. And escape velocity basically is minimum velocity needed in order to escape from a planet's gravitational pull. In other words, how fast, and I'm assuming that you launch away from the ground, but how fast do you need to launch the object at in order to escape from the Earth, for example, or the moon or the sun or what have you. And you can determine it using forces, but if you do it that way, you have to use calculus to solve. You basically it actually gets kind of thorny. But you can also do it using simple conservation of energy. And what you basically do is you say, how much energy do you need to launch from the Earth with? How much kinetic energy do you need to give to the object that you're launching, such that the total energy at Earth's surface is 0? So we take the gravitational potential energy basically to be negative, and we take the gravitational potential energy to be 0 if you're infinitely far away from the Earth. And if the total energy at the point that you launch from is taken as 0 with this negative gravitational energy, that also means that you'll have 0 energy when you arrive out at infinity. And so basically we say, how much energy do you need in order to have, how much kinetic energy, do you need to have in order to have 0 total energy when you launch from the Earth? And given the mass of the object, that also determines how much speed you basically need to launch with in order to escape from the Earth or the Sun or whatever other thing you're trying to escape from. So our desired end outcome basically is that we need to escape the potential energy well of the attractor. And that's the final condition. Final condition is we escape. That means that we can just keep going away from it and we never end up sort of turning around and heading back towards it. And that means that you have a final gravitational energy of 0, and that's equivalent to setting R final equal infinity. If that's a little bit difficult to follow, just remember that Newton's universal law for gravitation basically says that force of gravity can be taken as universal gravity constant times mass of the object times mass of the planet or star or whatever you're trying to escape from, divided by the distance between the object center and the planet center. So here's the center of the planet, here's the object. This distance right here would be r. Okay, so if you want to have a total escape from this, then you need this force to go to 0. So force of gravity is 0 when r is equal to infinity. And similarly, the energy, the gravitational energy, we might put as negative g m object m planet over r. And that's also equal to 0 if r is equal to infinity. So those are the conditions that we're basically solving for. All right, and so basically we're trying to get to r equals infinity at the same moment when the object ceases moving. That means it runs out of kinetic energy for escaping. And so that's where this condition of final energy needs to be 0, because you basically have run out of kinetic energy, but you've also escaped the planet and are infinitely far away, so you have 0 potential energy. So this is your condition for achieving escape speed. Okay, so those were the final conditions. What do we need to do for the initial conditions? Well, initially, you have the object somewhat nearer than infinitely far away from the attractor. The attractor is basically the planet, the star, the moon, the comet, the galaxy, whatever it is that you're trying to escape from. So that's expressed as r initial is less than infinite. So this is very often taken to be on the surface of the planet. So initially the radius might be whatever the radius of the planet is if you're sitting on the surface of the planet. Second condition is that the object needs to be moving away from the attractor. This diagram shows it moving directly away from the center, although the actual path might look like this. So the object doesn't necessarily need to be moving directly away in this sense. It can in fact be moving away in this sense, and everything will still work out. So in any case, that means you have a non-zero initial speed. So let's look at what the energy condition says. Well, the energy initially should be whatever the kinetic energy is plus whatever the potential energy is. Kinetic energy, of course, is half times the mass of the object times the initial speed of the object, where this speed is really given by speed with respect to the attractor, the planet or what have you. So this is the kinetic energy, and then we've set the potential energy as a negative, so that's universal gravitational constant times mass of the object times mass of the attractor divided by whatever the initial distance from the center of the attractor to the center of the object is. So the conservation of energy then requires that the initial and final energies be equal. And recall from the previous slide that our final condition was E final equals 0. So that means that all of this right here needs to be set equal to 0. So, and that's to get minimum escape speed. If it's greater than 0, then you're still going to escape. So at that point, you get an equation that looks like this. We've just set it greater than or equal to 0. And so if you want to solve this thing for the initial speed, you come out with an equation that looks like this. Vi is greater than or equal to 2 times g times mass of the attractor over the initial distance from the attractor with a square root around all of it. All right, let's work a few examples. And both of these examples say what is the escape velocity needed to escape from something, the moon, the Earth, ignoring air resistance. Of course, there's a whole table over here, table 7.3.1 we'll call it, which is showing approximately what the escape speeds should be. So the Earth should be 11.2 kilometers per second. The moon should be 2.3 kilometers per second. I'm not asking these questions just so you can look it up in this table. I've provided this table so that we can answer these two questions and then compare to the values in the table and see how well we do. All right, so what we would need to do here in order to actually solve this is we need to get the mass of the attractor and the initial radius, meaning the radius of the attractor. So for the moon, what are those values going to be? So we should go look up that information. So here is the college physics textbook from Openstax. If we go to page 1254, well, 1252, but 1254 of the PDF file, we get this nice table. This is table C3, solar system data. And sure enough, for the moon, we have a mass 7.35 times 10 to the 22 kilograms, and we have a radius 1.74 times 10 to the 6 meters. So let's go ahead and put those guys in. So our initial is basically that average radius, 1.74 times 10 to the 6th meters. The mass of the attractor is that mass of the moon, 7.35 times 10 to the 22 kilograms. So the minimum escape speed would be the equals to. So anything greater than or equal to 2 times g. Recall that g is about 6.67 times 10 to the minus 11 Newton times meters squared per kilogram squared times mass of the moon was 7.35 times 10 to the 22 kilograms, and then divide all that stuff by this radius, 1.74 times 10 to the 6th. Okay, so I'd say it's probably calculator time. 2 times 6.67 times 10 to the minus 11 times 7.35 times 10 to the 22 divided by 1.74 divided by 10 to the 6th. And now we take a square root. We come out with 2,373.8. Given that there's two significant figures, I'd say this is about 2,370, and the units are going to be meters per second. And if you want, you can convert that to kilometers per second, so 2.37 kilometers per second. So that is our minimum escape speed from the moon, which is, again, not so bad compared to the table. This one says 2.3. If I were to round, I'd get 2.4, so pretty good. So now let's do for the Earth, and we're going to ignore air resistance. So for the Earth, again, we're going to need to get the radius of the Earth, and we're going to need to get the mass of the Earth. And again, you can pull those up from that Openstax text, for example. So the mass of the Earth is given here, 5.9736 times 10 to the 24 kilograms, and 6.376 times 10 to the 6th meters. I guess they just feel like we need a couple extra significant figures here. Well, I am going to stick with 3 significant figures for G, so I might as well just write down 3 significant figures for both the Earth and mass and radius. Whoops, this is actually the mass of the Earth that I'm writing down right now. And so the radius in question is going to be 6.3, says 76, so 6.38 times 10 to the 6th meters. And so our escape velocity, again ignoring air resistance, should be 2 times 6.67 by 10 to the minus 11 Newton meters squared per kilogram squared, times the mass of the Earth, 5.97 times 10 to the 24 kilograms, divided by the radius of the Earth, 6.38 times 10 to the 6th meters. So that means that the escape velocity should be, let's pull out our calculator to do this, 2 times 6.67 times 10 to the minus 11 is a pain in the butt to put in on this calculator, times 5.97 times 10 to the 24, and then we got to divide all that by 6.38, divide that by another 10 to the 6th, and take a square root, and we come out with 11,172.6. So I'm going to round that off to a nice 11,200 meters per second, or if you want, 11.2 kilometers per second without air resistance. And if we look back on this table, it says that the escape speed for the Earth is 11.2 kilometers per second. So to within 3 significant figures, my answer and this standard answer from the table agree. So that's good news. All right, well, we've said that energy can neither be created nor destroyed, but that does leave that you can transform energy. So, for example, here's a solar aircraft, and it's taking in solar energy, Solar energy basically means energy from sunlight that's electromagnetic radiation, and then it's using that to generate electrical energy, which is running a motor. That's something that we'll actually learn about maybe next semester, how a motor works. But a motor generates mechanical energy. Another example is that you can make an engine. In an engine, you use heat, that's thermal energy. You raise the temperature and therefore the pressure of some fluid, generally speaking a gas, and then that does some work by expanding against a piston. And the work done by an expanding gas, if it's expanding under constant pressure, would be pressure times the change in volume over which it expands. So that's also equal to mechanical work. And of course, for the biomed majors out there, pre-med, biology, etc., life sciences, food is of course converted to energy. So you eat food, you burn the food, that generates energy within your body, and that enables your body to do work. So these are all different versions of energy being transformed. It's useful to know one last little thing, which is efficiency. Typically speaking, not all the input energy is going to be used in a given process, and in fact, not all the output energy is always useful. For example, you eat so much food and then you burn it off trying to do some activity like cycling or climbing. You end up only using 20% of the energy that you burn to actually do the work of cycling or climbing. 2% for swimming on the surface, 4% swimming submerged, etc. This, by the way, I suppose would suggest that swimming on the surface should burn the most energy. So I guess if you're trying to burn energy to lose weight, this table would be claiming that swimming on the surface is the best way to do that of these different options. You can see it compares favorably to everything from cycling or climbing to weightlifting. Moving on down the scale, you'll notice that there's some pretty efficient things here. An electric motor, 98% efficient. Gas heater for residential use, 90% efficient. That's pretty good. Steam engine, 17%. Most engines in your car are around 30 to 35%. Basically, these efficiency percentages have taken the work done by whatever it is, whatever source we've gotten the energy to do work, and we've divided that by the energy taken in. So in the case of exercise, for example, maybe you have stored some carbohydrates, or God forbid you have some fat that you're burning. Then according to this, for every joule worth of work that you actually do, you burn 50 joules worth of fat or carbohydrates or what have you, doing this swimming. And so compare that, for example, to the gasoline or diesel engine. So gas engine, 30% efficiency means if you burn a 1,000 kilojoules worth of gasoline in your car, you'll get 300 kilojoules worth of actual work done by the car. So I suppose by extension, if you could figure out how much the energy content of a gallon of gasoline is, then you can also figure out how fast you can make your car go from 0 to a final speed by burning through some amount of gasoline, etc. So that's all that I have for this part of the lecture. I hope that you've enjoyed this lecture and that you find it to be helpful. And as always, I wanted to put up this nice screen of credits showing where I get all of my charts, tables, figures, etc. from, at least the ones that I don't generate myself. Thanks for watching.